Hello everybody, welcome to today's video. Today we'll be doing something a little bit different. We're going to talk about polar coordinates. So this is just a different system that we can use to plot points on a plane. So we'll get into that. We'll introduce the polar coordinate system and look at its grid. It will be a little bit different. Instead of looking at rectangular coordinates, which we can use by building rectangles, polar coordinates will have these concentric circles. So we'll use that to plot some points. We will convert some polar coordinates to rectangular coordinates and vice versa. We'll go from rectangular back to polar coordinates, and then we'll transform some equations between the two forms, because we can actually just write equations in terms of this polar coordinate system, which can be kind of nice. So let's get into it here. First, we're going to just introduce this system. So we usually plot points on the Cartesian plane using rectangular coordinates x and y, meaning that you would travel some distance in the x direction and some distance in the y direction, and you would find wherever your point lives in relation to the origin. Instead of doing that, there is another way to do this. Polar coordinates are labeled r theta. So we're going to look at r some radius, and then some angle theta to travel to find the spot that we're trying to get to. So the polar grid is represented as a series of concentric circles radiating out from the pole or the origin. So that is where the name comes here. The polar coordinates, we're thinking about starting at some pole. We're going to travel out some distance r, and then we're going to swing it around some angle theta to find the point that we're looking for here. So let's look at some examples in action. So if I want to plot the point 2 pi over 4, that means that from the pole, maybe I should actually just label this circle here first. Each one of these little rings here corresponds to a radius distance. So I'm just labeling 1, 2, 3, 4, 5, 6, 7, and I could label them in the negative direction too. -1, -2, -3, -4, -5, -6, -7, and same in the y, or what we would typically call in the rectangular coordinate system, the y direction, and the other way too, -1, -2, etc. And then I can also label some angles as I go around here. This is, of course, 0. This is going to be pi over 6. This is going to be pi over 3. Up here we've got pi over 2. We got 2 pi over 3. We've got 5 pi over 6. Over here we've got pi. And then we've got 7 pi over 6. And 4 pi over 3. At the bottom here we've got 3 pi over 2. And then we've got 5 pi over 3. And 11 pi over 6. So just to label some things on here, if we need pi over 4, then we might need to just, rough it in or something if we want to, which is what we want on this first one, now that I'm re-looking at the problem. So if I want to plot this point 2 pi over 4, what we can do is start by looking out a distance of 2, or we know that we're going to be on this ring. And of course there are in-between rings here as well. If we want something between 3 and 4, we might have to imagine another ring in between them. These are just reference rings. And then I want to go up to pi over 4, and pi over 4 is going to be in between pi over 6 and pi over 3. So if I wanted to draw in another reference line here for pi over 4, I could, but we don't always absolutely need to. But there we go. There's the point 2 pi over 4. And we will label some other ones. So this one, maybe I can just color code. That one's the green. I can switch to blue for this next one here. So if I want 5 pi over 2, we're going to look at a distance. Well, in practice, we might actually look at the angle first. We want to swing to this angle of pi over 2, and we want to go out a distance of 5. So 1, 2, 3, 4, 5 is going to be right there. So here is the point 5 pi over 2. If we want now the point 3, 7 pi over 6, what we can do is look at this line, this reference line here that's associated with 7 pi over 6, and we just want to go out a distance of 3 from the pole there. So here is the point 3, 7 pi over 6. Now the last one here is a little bit weirder because it has a negative value in front of the radius. So there's several different ways that we could think about doing this. We could either first start as going out to -4, so in the negative direction, and then rotating pi over 3 from there, which would put us right here. So here we went out in the negative direction and then traveled a distance of pi over 3 from there in the usual direction. Or what we could do is go to pi over 3 and go out 1, 2, 3, 4. So here is positive 4 pi over 3, and then you can go back through the origin the other direction, the same magnitude. So back towards here, back through the other way, and we get to the same spot that I referenced before. So just a couple different ways to think about getting this value here of -4 pi over 3. And it could also be the case that sometimes the angles are negative, and then you'll travel in the opposite direction as well. So there we go, just some different examples. Let me erase that one because that was not the one we wanted. But just some different examples here of how to plot polar coordinates on the polar coordinate grid here. So next we will look at converting from polar coordinates to rectangular coordinates. So to convert, we are going to need to use these relationships here. We're going to actually be adding to this list of relationships as we work through these sections. But the first thing that we want to do, and these are just our normal relationships. We saw these in the last video, actually. Cosine is the adjacent over the hypotenuse, which is going to be the radius of whatever circle we're looking at. And so we could rearrange this, multiply both sides by r, and we would get something of that form. And same thing for sine. So if I want to write the polar coordinates, 3 pi over 2 as rectangular coordinates, well, we can think about where that lives. So thinking about this as a polar coordinate system, I could travel up or travel around pi over 2, and that would put us on what we would consider the y-axis on a rectangular coordinate system. And then I would travel up 1, 2, 3, and this would put me at the point 0, 3. So that is what my prediction is going to be, but of course we're not always going to have nice points like this that happen to live on one of the axes. So let's look at how we would do this algebraically. We're going to use these relationships here, that if I want to find the x value, I want to convert from r theta to xy. Well, I know that x is going to be r times the cosine of theta. The r is 3 times the cosine of pi over 2. The cosine of pi over 2 is 0, so I've got 3 times 0, and that is equal to 0. So our x value here is going to be 0, as we predicted over here. To find our y value, we will do r times the sine of theta, which is going to give me 3 times the sine of pi over 2. And the sine of pi over 2 is 1, so we're getting 3 times 1, which is 3, and that is going to be our y value, just as we predicted on our picture over here. So in a rectangular coordinate, I'll just write rectangular coord. We're going to get the point 0, 3, just as we predicted from our picture. So there we go. We have converted this polar coordinate to a rectangular coordinate, and we can see that they hit the same spot on the axes here. Let's look at another example here. Here we are looking to write the polar coordinates -1, 2 pi over 3 as rectangular coordinates. So just to maybe think about what this looks like on a graph, 2 pi over 3 is going to be around here. So we can think about traveling 2 pi over 3, and we could go out a distance of 1, and then we could travel back through to get to this point over here. So that's where we're looking, but I actually have no idea where that is. Well, I kind of do, because since we're looking at a radius of 1, we're on the unit circle, so I do have some idea of where that might be. But let's look at it using the relationships that we have here. So again, this is the point r theta. We've got these relationships above here. We know that x is going to be r times the cosine of theta. So that's going to give us -1 times the cosine of 2 pi over 3. And the cosine of 2 pi over 3 is -1/2. So here we are getting x to be positive 1/2. So there's our x value. And our y value is going to be r times sine theta, which is -1 times the sine of 2 pi over 3. which is negative 1 times square root of 3 over 2, which is going to give us negative square root of 3 over 2. And that is going to be our y value. So we've got the xy pair here in rectangular coordinates. Whoops. Coordinates. We're getting the point 1/2, positive 1/2, negative square root of 3, negative square root of 3 over 2. And just to think about my picture over here, if I erase a little bit, like we said, we knew that we were going to travel a distance of 1 from the origin here, which actually does give us, if I can kind of get it in here, a unit circle. And if we're thinking about this angle here, which is, I don't know, negative pi over 3 or 5 pi over 3 if we want to go around the other way. But since we're on the unit circle, this is the point that we are familiar with, which is 1/2 for cosine and negative square root of 3 over 2 for sine. So just thinking about this in context of the problem just confirms my solution over here that this is definitely the point that we thought it was. So there we go. We have converted these polar coordinates to rectangular coordinates. Next, we will think about going the other way. So here we are starting with rectangular coordinates, and we want to switch them to polar, which is a bit of a more difficult process. Just using these straight relationships to go the other way can be nice. But going back the other way, we might need to be a little bit more creative on some of these. So we have some other relationships to look at. So we've got r squared is equal to x squared plus y squared. That is the formula for a circle. So we can always use that relationship to convert to whatever we want to. And we'll also throw in the fact that tangent is y over x, just so that we can use that relationship as well. So now we've got there's 2 embedded in each one of these. So there's 4, 5, we got 6 different relationships that we can use to try and do this. So the first thing I'm going to do, remember now that we have polar coordinates, this is x, y. So we know that tangent, or maybe I should say that our goal here, I should write this down first before I hop into it. Our goal is to get this as just r and theta. So we're going to get our theta by using the tangent of theta here. So that is why we are using tangent theta. And we're using tangent theta instead of sine or cosine or something because we know what the x value is and we know what the y value is. So this is going to give us 3 over 3. Which is equal to 1. So we're looking at the tangent of theta being equal to 1. And if we solve this, we will get that theta is equal to either pi over 4 or 5 pi over 4. Since tangent is positive in both the first quadrant and the third quadrant. But we know which quadrant we are in. We are looking at the point 3, 3. So, 1, 2, 3, 1, 2, 3. We're definitely in the first quadrant over here, which means that we can throw that one out. The angle that we were looking at is definitely pi over 4. It's all right. Because we're in quadrant 1, we can cross that one out. Or maybe I should point to the other one. Point here. We're crossing the other one out because we're in quadrant 1. So we're going to take our angle to be pi over 4. But depending on the context of the problem, if you knew that we were looking at perhaps negative 3, then we would be over here instead, and then we would use this angle instead. But here's the one, or here's the one we're using for now. Okay, now we've got our angle. We have found theta. So here's find theta. And now we want to find r. So to do that, we are going to look at this relationship here, and I could actually take the square root of both sides. To even get another form here, I guess, that r is equal to the square root of x squared plus y squared. So that's what we're going to use. R is equal to the square root of x squared, which is 3 squared. 3 squared plus y squared, which is 3 squared. So we're getting r is equal to the square root of 9 plus 9, which is 18. So r is equal to 3 square roots of 2. And there we go. There is the other value that we need. So if I want to write this in polar coordinates now, this is the point 3 square roots of 2, comma, pi over 4. And if I wanted to think about some circles here instead, we'll get rid of that. And we're looking at 1, 2, 3. I'm going to put a fourth one. Oh, that's a terrible circle. I guess I could have used the computer to do any of these circles. But 3 square roots of 2 is just past 4. So we're going to go to pi over 4 and then go out 1, 2, 3, 4 and go a little bit more. So there is the point. 3 square root of 2 pi over 4 on our polar coordinates here. So there we go. Takes a little bit more effort and creativity to get what we want, but we've got it there. All right, next we are going to look at rewriting some Cartesian equations in terms of x and y in terms of polar equations. So a polar equation is in terms of r and theta, and our goal, if we can, maybe I'll write this down, our goal is to write r, or maybe I should say even before that, we want to eliminate x and y and write r as function of theta, meaning getting something that looks like r of theta equals, and everything in there will be in terms of theta. So that's our goal here. So we're looking at the equation x squared plus y squared equals 6y. I'm noticing straight away that we've got an x squared plus y squared in here, so I can just straight rewrite that as r squared. So maybe just to start writing things here, x squared plus y squared equals 6y, rewriting the problem. But now I know that this is r squared is equal, so now I've gotten rid of that x and y. I still have a y over here, so I think to get rid of that, I will use this relationship between y and r sine theta. So this is going to be 6 times r sine theta. I'm trying to get this as r in terms of theta, so let me get all the r's on one side. Let me subtract 6r sine theta from both sides. And now that'll be equal to 0. And I can factor out an r. So I'm getting r times r minus 6 sine theta equals 0. So using the zero factor property now, this tells us that either r equals 0 or r minus 6 sine of theta equals 0. Well, r equals 0 just gives us a single point. It just gives us the point, the pole. It just gives us 0, 0. So we will throw this out. This is not giving us a full equation. It's just giving us one of the points. So I'll just write that down. This only gives the pole. But what this tells us is that our function must go through the pole, or must go through the origin. But solving this guy over here, I can just add 6 sine of theta to both sides, and we actually get what we want, that r is equal to 6 sine of theta, and now I have r written in terms of theta. So if I really wanted to be explicit about this, I could say that r of theta is equal to 6 sine of theta. And there is our new function as a polar equation. And for what it's worth, the graph looks like a circle sitting right on top of the origin here. So there's the point that we knew it went through. We knew it went through the pole, and the circle just lives on top, and it's got a radius of 6. So there we go. We have rewritten this Cartesian equation as a polar equation using these relationships above here. So let's try another one of these. We want to rewrite this equation here, y equals 3x plus 2, as a polar equation. So again, our goal is to write this as r as a function of theta and get rid of all these x's and y's. We know that this should look something like plus 2, slope of 3, so something like this, which is kind of interesting because we are dealing with cosines and sines, which typically help describe circles, but we're going to put them together in such a way that no circles or squiggly bits exist. We just get a straight line. So to do that, we are going to take y equals 3, 3x plus 2, and I'm going to rewrite x and y in terms of r cosine theta and r sine theta. So what I'm getting here in my first step is that r sine theta is equal to 3 times r cosine theta plus 2. I'm trying to get r in terms of theta, so let me get all the r's on one side and see if I can't isolate that somehow. So I'm going to subtract 3r cosine theta from both sides, minus 3r cosine theta. Here they're canceling. So now what I've got is r sine theta minus 3r cosine theta is equal to 2. I can factor an r out since they both have an r in them. So I've got r times sine theta minus 3 cosine theta is equal to 2. And now I will divide both sides by everything that's not r. So I'll divide both sides by sine theta minus 3 cosine theta, sine theta minus 3 cosine theta, so that they cancel on the left-hand side, and what we've got left here is exactly what we want. We have r in terms of theta, and this is going to be 2 over sine theta minus 3 cosine theta. And there we go. We have used some of the relationships above here to rewrite our Cartesian equation in terms of a polar equation and just r and theta. So there we go. We are going to now go the other way. So now we are given a polar equation and we want to rewrite this in terms of a Cartesian equation. So again, we're just going to use some of these relationships we got above here to try and see if we can't go back the other way. So here we want to, just like last time, eliminate not x and y, but we want to eliminate r and theta and introduce x and y. So this is our goal. Eliminate r and theta. Maybe I shouldn't use that symbol twice. And introduce x and y. Okay, here. So the first thing that I'm noticing is we have, so maybe just let me rewrite it. R equals 3 over 1 minus 2 cosine theta. I think the first thing that I want to do here, I know that there's both r and theta, but let's think about theta first. And I know that cosine theta is the same as x over r. So let me make that substitution first. And I will get that r is equal to 3 over 1 minus 2, and I'm rewriting cosine theta as x over r. So from there, I can multiply both sides by the denominator here. So let me multiply both sides by 1 minus 2x over r. 1 minus 2x over r. So that they cancel on this side. And I've got, maybe I'll just move it up here. And I'll distribute maybe, well, let me write it out so it looks clearer. 1 plus 2x over r is equal to 3. And now as I distribute this r here, I'm going to have r, but they're going to cancel with the 2x over r. So I'm just going to have plus 2x is equal to 3. Oh, that should have been a minus. That should have been a minus. That should have been a minus. Just a typo there. Just a typo. No reason other than it was supposed to be minus the whole time. I just messed up. So there we go. Now we'll add 2x to both sides, and I'll get that r is equal to 2x plus 3. And now I need to get rid of this r and turn it back into an x and a y, and I have this relationship here, which also tells me that r is equal to the square root of x squared plus y squared. So I think that that will be, well, I could use that if I wanted to, I suppose, but let me actually square both sides now that I'm looking here. This would actually be nicer if I squared that side and squared that side. Then I will get exactly r squared, so then this will be x squared plus y squared is equal to 2x plus 3 all being squared. So there we go. There's a nice way. And you could have used this other version here. I just thought that this might be a little bit nicer. That way there's no square roots or anything in there. Let me write that 3 a little bit better. But there we go. We have written this polar equation as a Cartesian equation in terms of x's and y's. So let's take another a look at a different example here of doing the same thing. We want to rewrite this polar equation as a Cartesian equation. Here what we've got is r sine of 2 theta. So we don't know anything about relationships for sine of 2 theta, but we do know a double angle formula. So the first thing I'm going to do is rewrite r is equal to sine of 2 theta as r equals 2 sine theta cosine theta. So that's using the double angle formula. And I have relationships, like I said, for cosine theta and, well, I shouldn't use those ones. I should maybe use these ones over here for cosine theta and sine theta. So now I can rewrite this as r equals 2 times sine theta, which is y over r, times cosine theta, which is x over r. So what I'm getting is r is equal to 2xy over r squared. So we're trying to just get this in terms of x's and y's. Let me multiply both sides by r squared so that they're canceling here. And now we've got that r cubed is equal to just 2xy. Now, what I'm going to do, I've got something in terms of r squared here. I'd really just like an r cubed, but I'm going to just get r. So now I will do this simplification here and plug in r as the square root of x squared plus y squared. So in my next step here, I'm just rewriting r as the square root of x squared plus y squared, and then I'm going to cube it. So maybe I can color code here. I'm still going to need to cube it, and here is me cubing it. And this is going to be equal to 2xy. So what I plugged in here was r, and then I'm still cubing it. What I plugged in was r, and then I'm cubing it. And then we could just rewrite this a little bit cleaner as x squared plus y squared to the 3/2 power. Just kind of combining that power and the square root. Square root we could write as 1/2. And this is a little bit nicer here. I mean, this is a fine answer, but if I wanted to rewrite it, I could rewrite it this way. And this is another perfectly fine answer. Or you could multiply, or you could raise both sides to the 2/3 power to get rid of it on the left, and we would get 2xy raised to the 2/3 power on the right. So these all say the same thing, just different rearrangements of each other. Each one equally valid. I would be happy with any of these here. So here we have rewritten this polar equation again as a Cartesian equation in just a few different ways. If you put any of these into Desmos or something, you would see that they should all give the exact same graph. So there we go. It looks like it is time to practice. So good luck with the homework. If you have any questions, please let me know. I am always happy to help you. I'll see you in our next video.